Hello and welcome to the session on functions. What are we going to learn in this session? First, we'll try and understand what do we understand by this term functions. Second, we'll try and understand how to calculate the value of different functions for different inputs. And finally, we'll understand what are composite functions and inverse of any function. So let's get started then. What is a function? For that, let me give you a couple of statements. Your health depends on your eating habits. What does that mean? That depending on what you eat, you will have a health of that quality, right? Which means your health is a function of your eating habits. Time taken to cover a certain distance depends on speed. What does that mean now? Well, it means depending on the speed, you will be able to know how much time you will take to cover a certain distance. Well, which means the time taken to cover a distance is a function of the speed. So it's clear that wherever we use the word function, there's a kind of dependency between two quantities. For example, in the first case, where we say health is a function of eating habits, we imply that health depends on your eating habit. Likewise, in the second case, because time is a function of speed, we imply that the amount of time taken depends on the speed. But how are the two examples different? In the first example, there's not a specific or a direct relationship between the eating habits and health because it's affected by a lot of other factors. And hence, you cannot really predict your health depending on what you eat. Correct? Whereas in the second case, because there's a specific relation between speed and the time, you can actually predict the time taken. Okay, because you know that time taken is distance upon speed, right? Because there's a specific relation, we can actually predict the time. And hence, the first example of eating habits and health cannot be classified as a function because there's no rule binding eating habits and health. Whereas the second example, speed and time taken, can be classified as a function because there's a rule which binds both of them. Let's look at one more example. Okay, let's say there's a candy vending machine versus a snack vending machine. How are the two of them different? Well, in a candy vending machine, if you input a coin, it can randomly give you any candy. Can you predict the output? Not really, right? Because the machine can randomly dispose any one candy, whichever color, right? It randomly assigns one candy. Whereas in a snack vending machine, we input the coin and also a specific number. The snack which is given to us represents that specific number, right? A specific snack is given corresponding to the required input, right? Which means you can actually predict what snack can come out because you are the one who is inputting the number. So in the first case, it's not classified as a function because one input can give you many output. It could be any of the colors that can come out, right? The candy could be of any color. There's no specific output. You cannot predict it. But in the second case, you can specifically predict it because you have entered the number. So that is the snack that will come out, right? So that can be classified as a function because one input and the specific number has a specific output, right? With these two ideas in mind, let's now try and understand, okay, which of them is a function and not a function based on everyday examples. So while a passport or a vehicle or even for that matter a consignment, okay, they have specific numbers which we can relate to a specific person or a vehicle or even a consignment. Still, there's no rule binding that, right? We cannot predict that if this is the number, this should be the person whom passport can belong to, or this is the number, this is the car. We cannot predict it. There's no rule. Whereas in the examples like a lawnmower or even the calculating machine which you can see on uh, the counters of various stores, we can actually predict, if one article costs so much, so many, 10 of them will cost how much? Or if lawn mowing speed, I know that if in 1 hour I can mow so much area, to mow the entire lawn, how much time will it take? So I can predict because they are defined by some rule, right? So then we go on to define the function as a function is the relationship between two sets of numbers. The numbers that go into a function are called inputs, and the numbers which come out are called outputs. And the most important one is there's a rule which assigns every input to exactly one output, which means there are two things which are important to define a function. One is the rule. There should be a relationship between input and output. There should be a specific rule which helps us to predict the output. And the second one is there should be one output corresponding to every input, right? For example, if the inputs are 2, 4, and 8, and the function, the relationship, the rule which says is add 11, you can predict the output, right? 2 plus 11 is 13, 4 plus 11 is 15, and 8 plus 11 is 19. You can predict the output. Well, that's a function then. The example that you saw earlier is an example of a function machine. Okay, what's a function machine? A function machine is a diagram that represents a machine that takes an input, applies a rule, such as a set of operation, and delivers the answer as an output. It's as simple as that. For example, we can have one step function machine where there's one rule. So divide by 3 is the rule. So what will be the output for each of the inputs which are given? So 3 divided by 3 is 1, 9 divided by 3 is 3, and 21 divided by 3 is 7. As simple as that. We can have two-step function machines as well, wherein there are two rules which follow each other. For example, the first rule says subtract 1. After that, we need to multiply by 2. So for each of the inputs, what will be the output? So 5 minus 1 is 4, times 2 is 8. For the second input, 8 minus 1 is 7, times 2 is 14. And for the third input, 9 minus 1 is 8, times 2 is 16. Right? So these are called function machines. Sometimes in a function machine, you are required to find the rule. So can you predict the rule in each of these cases? 7 linked to 14, 20 linked to 27, and 25 is linked to 32. Well, you guessed it. It's add 7. In the second example, what do you think is the rule? 20 linked to 4, 35 to 7, and 50 to 10. What links each one of them? Again, you predicted it correct. It's divided by 5, right? 20 divided by 5 is 4, and so on. 35 divided by 5 is 7. So it's divided by 5. At times, you may also have to find the input. It's just the reverse. So you are given the output. You're given the rule. How can you find the input? All you need to do is you need to inverse the operation. So the rule says multiply by 6. To find the input, you need to just inverse, which is divide by 6. So 24 divided by 6 is 4, 66 divided by 6 is 11, and 102 divided by 6 is 17. Okay, how can you do this for the two-step function machine? If you're given the output, you first inverse the first step. In fact, when you're reversing, it's the second step. So plus 3 becomes a minus 3. So we find the intermediate outputs, which means 23 take away 3 is 20, 39 minus 3 is 36, and 51 minus 3 is 48. And then we inverse the other step. So multiplied by 4, the inverse of that is divided by 4. So each of those will be divided by 4 to get your corresponding inputs. So 20 divided by 4 is 5, 36 divided by 4 is 9, and 48 divided by 4 is 12. There you go. Now, in general, the function machines are not the only ones which are classified as function. There are specific representation for function. Let's understand these now. So as you know, a function links an input to an output, and a function is a rule, correct? Normally, in maths, the input is represented by the letter X and the output by the letter Y. So let's assign a rule between X and Y. So Y equals to X squared plus 7. So the rule is whatever is the input, you square that, you add 7 to give the output. So your output is input squared plus 7. That's your rule. So for each of these inputs, is it possible to find the output? Well, all I need to do is square the input and add 7, right? That's your rule, which means y is actually square of x plus 7. So y is dependent on x, as you can see, correct? Because the value of y depends on what your input is. It depends on x. And hence, we can always say y is a function of x, right? The output is a function of the input. Now, this is represented in a specific manner. It's represented as y equals to f of x, indicating that y is a function of x. The f in fx is the function, correct? Domain is a term referred to all the input values, okay, whichever values the input can take, whereas range is a set of values that the output can take, correct? And we can write the function as y equals to f of x, which in this case is linked by x squared plus 7. Now, how to find the value of any function for an input? For example, if f of x is defined as 2x plus 3, can you find f of 7? To find the value of any function for a particular input, we use the same rule as a substitution, right? In a football, you can always substitute players. What does substitution mean? You replace jersey number 9 by jersey number 12. So 9 goes out and is replaced by 12, right? Likewise, when we are finding the value of a function, all I need to do is replace x by the input. In this case, the input is 7. We need to find the f of 7, which means the input is 7. So we replace x with 7. So if I replace x with 7 on the left hand side, you'll get f of 7, which is exactly what we need. And if I replace x with 7 on the right hand side, you'll get 2 times x, which is 2 times 7 in this case, plus 3. How much is 2 times 7? That's 14, plus 3 gives you 17. So f of 7 is 17, right? It's easy to find the value of any function. All you need to do is replace the variable, input variable, which is x, by that specific number. Let's take one more example. This time, it's a quadratic function. So f of x is x squared plus 4x minus 2. Find the value of f of 3. So what's the replacement that we need to do in this case? We need to replace x by 3, right? Because in this case, we need to find f of 3. So we need to replace x with 3. On the left hand side, if I replace x with 3, we get f of 3, which is what we need. Likewise, we need to replace x with 3 on the right hand side as well. So we get x squared, which is 3 squared, plus 4x, which is 4 times 3, minus 2. 3 squared is 9, plus 4 times 3 is 12. 9 plus 12 is 21, minus 2 is 19. So f of 3 in this case is 19. So that's how we find the value of any function. Right, let's end the session with two concepts. One is composite functions and two is inverse of a function. What are composite functions? For this, let us define two different functions. Okay, so let's say f of x is x plus 3 and g of x is 2x squared plus, it's 2x squared, right? There are two different functions. So the output in the first case is f of x and the output in the second case is g of x. How is the output linked to the input in the first case? It is input plus 3. So whatever value x takes, you add 3 to get the value of y. Right? So input plus 3 is your output. But Whereas in the second case, the output is g of x, which is nothing but 2 times the square of the input, right? Because if x is the input, you square it, x squared, multiplied by 2 to give 2x squared. So whatever is the input, you square it and double it to get the output. So far so good. Now, how do we define composite function? Let's say we have f of x, and the output of f of x is fed into g of x. What do we get? Right. So as you can see, if the input was x, right, into g, the output was g of x, right? If I input the variable x into the function g, you get your output as g of x. But what did we input in this case? In this case, the input to gx was not x. It was the output of fx, which is fx, right? Output of fx is fx. So fx goes into gx. So the output in this case will be g of fx. Now this is what we call a composite function. A composite function is simply a function of another function, right? This is a function because g is performed on fx. G is not performed on x. Had x been the input, the output would have been gx, correct? But x is not the input. Fx is the input to gx, and hence g is being performed on fx. That makes it a composite function, simply function of another function. Now, how do you find the value of this composite function? For that, let's track right from the beginning, okay? Fx, it's like a two-step function machine, okay? So f of x is input plus 3, correct? So whatever is the input, you add 3 to get the y, the output. So in this case, the output would be x plus 3. The input is x, the output will be x plus 3. What does g of x do? Okay, it does input square and doubles it. Okay, we have defined it earlier. So whatever is the input, you square it and double it. So if the input was x plus 3, the output will be x plus 3 the whole squared times 2, right? So g of f of x is actually twice of x plus 3 the whole squared, right? Now let's do something interesting. This time we'll just reverse the flow, which means we'll input x into gx, and whatever is the output, we'll feed it to fx. Just reverse. Let's see what happens. So we'll first input x to gx. Output will obviously be gx, which is now going into fx. Now, if the input was x, the output would have been f of x from output. But the input is not x, the input is gx, correct? So the output in this case will be f of gx. Remember, g of fx is different than f of gx. G of fx, which we saw earlier, is a function g being performed on fx, whereas f of gx is a function f being performed on gx. It's just the reverse, correct? Now, how do I find the value of f of gx? Well, let's track it from the beginning. What does gx do? It does input square and doubles it, right? Whatever is the input, squares it and doubles it. So if x was the input, the output would be 2x squared. What does function machine f does? Okay, f it simply adds 3 to the input and gives us the output, right? X plus 3 is whatever is the input, add 3, gives the output. So if the input was 2x squared, what will it do? It will just add 2x squared plus 3, right? It adds 3 to 2x squared and gives us the output. So f of gx can be represented as 2x squared plus 3, right? These are composite functions. Now finally, let us understand what do we understand by inverse of a function. It's just like changing the subject of a function, okay? So inverse of a function is the same as function expressed with x as the subject instead of fx. Inverse of a function reverses the effect of any function. It's as simple as that. And inverse of a function is represented by f to the power minus 1 of x, right? Now, what are the steps we need to do to find inverse of any function? Let's understand. Let's take a simple one-step function. F of x is x plus 10. Right? What it means is the input is x, the rule is plus 10, and the output is fx, which is x plus 10, correct? So in simple diagrammatic form, the inverse of that function has to be minus 10, right? So if I need to find the inverse of that function, I just need to reverse the process. So x minus 10 will be the inverse of the function. Now, how do we get that from the equation which is given to us? So it's the same as changing the subject of any formula or equation. Remember, we did this in one of the previous lessons. Because we need to make x the subject, we'll first highlight x with a different color. Now I need to ensure that everything apart from x goes on to the other side of the equal to sign. So in this case, x has a plus 10 on its side. So I need to negate the effect of plus 10. For that, I need to subtract 10 on both sides. So on the right hand side, I'll have x on its own. On the left hand side, we'll have fx minus 10. The last step to find inverse is to replace x by f inverse of x and to replace fx by x. Make sure you make a note of this. So once you change the subject to x, the last step you do is replace x with f inverse of x and replace fx with x. So your final answer would be f inverse of x equals to x minus 10. Okay, let's do this with a little difficult two-step function. So let's say f of x is 3x minus 5. First, let us represent this using a function machine. Okay, so what happens? Whatever is the input x, you first multiply that by 3, right, to make it 3x. Then you subtract 5, right, minus 5 to give the output which is fx. What if I need to inverse the effect? Okay, we have learned this earlier. All I need to do is start with x. Instead of minus 5, you do plus 5. Instead of multiplied by 3, you do divide by 3. And simply you get f inverse of x, right? It's just the inverse of fx. How do we do that? Using the equation which is given to us. As you know, all I need to do is change the subject of the equation to x. So let's highlight x with a different color, right? Now we have 3x minus 5. The first step is to take the 5 on the other side. For that, I need to add 5 on both sides of the equation. So minus 5 and plus 5 on the right hand side makes it 0. And on the left, we have fx plus 5. So on the right, we are left with 3x. And on the left, we are left with fx plus 5. Now, how do we get rid of 3? Because we need x on its own. Remember, we need to change the subject to x. For that, because 3 is getting multiplied to x, we'll divide by 3 on both sides. So we get x equals to f of x plus 5 divided by 3. Because if I divide the entire expression fx plus 5 on the left hand side by 3, we'll have entirely both the terms getting divided by 3. So x will be fx plus 5 divided by 3. And the final step to write it in the inverse form, remember, you replace x with f inverse of x and you replace fx with x, correct? So your final answer would then be f inverse of x equals to x plus 5 divided by 3, which is exactly the same thing which we can see using the function machine representation. Well, that was the session. I hope you understood the concepts taught in this particular lesson. Okay, we learned three things. First, we understood what do you understand by the term functions. Then we understood how do you find value of a function for a specific value of input. And finally, we learned about composite functions and inverse of any function. Thank you.